Hey everybody, welcome to our Design of Experiments presentation. My name is Jake May and my group members were Ethan Schwartz, Garrett Neal, and Mark Perry, and our experiment dealt with looking at the hydraulics in the mini excavator that the college has. This is an overview of the contents of our presentation, including the purpose of the experiment, our background information, the theory that we used, along with the task performed and our preparation that we did before the lab, experimental data, and results and conclusions. The purpose of the lab was to estimate the weight of various known loads using the pressure in an isolated hydraulic cylinder on the excavator and compare that to the known value of the weight. We also wanted to compare the measured extension and retraction velocities to calculate values using hydraulics equations. Here's some background information, including the model of the excavator that was used along with its weight. There's also some engine specs, such as the displacement, which is 104 cubic inches, the horsepower, which was 24.8, and the engine had auto engine speed control along with load sensing and flow sharing. There's also some pump specs on this slide, which was the flow rate of 26.4 gallons per minute and the max pressure, which was 3,553 psi.
So some governing equations we got from our hydraulic textbook are pressure, the extension velocity, retraction velocity, and our known equations of static equilibrium where sum of forces equals 0 and also sum of the moments are equal to 0. Some tools that are required for this experiment is a 2-foot level, measuring tape, calipers, and there are a few apps that you're going to have to download, one of them being Angle Meter 360, and this one's used to calculate the angle between the stick cylinder and the stick of the excavator. This will help you whenever you calculate your forces on the cylinder. And the next one will be used to measure the time it takes to retract and extend the bucket arm. And for iOS devices, you'll be using stopwatch camera, add to move movie. And Android, for Androids, you'll be using video stopwatch. As for safety, we do the PPE first, which you would have pants, boots, hard hats, and protective eyewear. You're going to need to watch the pre-operation videos that UGA will provide you. Also, when you start up the vehicle, that will be covered in the pre-operation videos. In operation, you need to familiarize yourself with what joystick does what before you start operating the excavator. When parking the excavator, you need to relieve the hydraulic pressure, and you do this by resting the bucket onto the ground and turning off the machine, and you need to do it in standby mode, which is not a full crank, and then take the joysticks, rotate them in full range of motion to relieve the hydraulic pressure that has been built up in the lines. So our tasks performed are safety, and I just went through those with you, and research. And we did research by looking at part manuals and service documents. We also had contacts with Caterpillar to give us a little bit of insight of what kind of experiments we need to do. We learned how to drive the excavator, and after that, we kind of brainstormed about what experiments we could do after driving it. When we figured out we wanted to do this experiment, we had to measure the fittings and order those parts. And when we did that, we decided that we needed to write down all of the procedures that we needed to take when we did the lab so that we had some type of guidance to go by. And after that, we completed the experiment with its rigging, and we took the measurements that were needed. And after we did that, we did this static analysis and dynamic analysis and calculated our error.
The theory behind the static portion of the lab was to isolate the stick cylinder on the excavator and then attach different loads and use the pressure measurement to predict how much weight the excavator was carrying. So to do this, we extended the boom cylinder so it was completely vertical and then retracted the stick cylinder so that it was level with the horizontal and defined this as the experimental location so that we could return to it for each load to have uniformity. To do this, we attached a 2-foot level to the stick and could see the bubble from the ground to ensure that we were getting back level on every single load. And the first thing that we had to do to make this as accurate as possible was to develop a calibration load, which was a no load situation in which just the arm of the bucket was lifted to the experimental height and the pressure was read, and then that pressure was then used on every other load that was attached, and the pressures were subtracted from each other to develop the pressure needed just to lift the load itself and not the arm of the excavator. And then using this pressure along with the geometry and the static setup that we developed, we could predict the weight that the excavator was carrying and then compare that to the known load of the weight that was predicted before the lab started. For the dynamic loading, the idea was still to isolate the stick cylinder. So the same position that was used in static was used in the dynamic, except for here, we would take the stick cylinder from fully extended to fully retracted and vice versa, and measure the time it took to go from one or the other. And using the time along with the stroke length that we measured, we could develop an experimental velocity of the stick cylinder and then compare this to the velocity values predicted by the hydraulics equations that were mentioned earlier. And then by comparing them, could figure out what the error was and how far off our experimental was from the theoretical. Moving forward, the results of the lab were very dependent on the different values shown in these tables. Most of these were measured by us off of the excavator and also were given in the spec manual. So these would be the diameter of the bore, diameter of the rod, stroke length, flow rate, angle that the piston made with the vertical, and then the various links that were used in the statics equations to be able to predict the weight that the excavator was carrying.
Now for the results of our lab, the static loading portion, the first load that we added was no load, and this was to examine the weight of the arm in the excavator that we could use as a calibration tool. This gave a pressure reading of 250 psi and induced a force on the piston of 1,333 pounds. And we calculated this weight to be 214 pounds. We then subtracted this 214 pounds from all the other subsequent measured weights so we could find out what the actual measured load is of just what we added at the bucket. The next load was 5 buckets of water with a pallet and the rigging. This came out to be 290 pounds. This gave a pressure reading of 550 psi with a force in the piston of 2,933 pounds and a calculated weight of 257 pounds. This is a percent error of 11.3. Now next, the pallet rigging and then 10 buckets of water was 500 pounds weight, and this gave a pressure reading of 770 psi, a force in the piston of 4,106 pounds, and then a measured weight of 446 pounds, the percent error of 10.8%. Lastly, we decided to lift up the sandbag, which had an unknown weight, and this gave a pressure reading of 1,475 psi with a force on the piston of 7,865 pounds, and we calculated the weight here to be 1,051. Granted, this weight can change depending on the atmospheric conditions. On a rainier day, the sand is going to be more saturated with water, which means it's going to weigh a lot more. But on our lab day, it was sunny and hot, so our sandbag was mostly just sand. The results of the dynamic loading, we did 3 separate trials and averaged the times. That way we could have one value that we could use for each extension and retraction. The time that we calculated for extension was 2.95 seconds and retraction 2.74 seconds. Now comparing these to our theoretical values, we found a theoretical velocity using our hydraulics equations for extension of 784 inches per minute, and our calculated value that we measured in lab was 402 inches per minute. This gave us a percent error of 49, and then similarly for retraction, we had a theoretical velocity of 1,144 inches per minute versus the actual velocity of 433. This gave a percent error of 62%. You will note that the extension and retraction velocities are not the same, and they're, the time that it took to do those ranges of motion were not the same, and that is because the volume of the piston on the retraction motion is lower than the volume required for extension, and so that means you need less fluid, and less fluid means you can do it faster. Now some sources for error for the static, which was 10.8 and 11.3 percentages, respectively. We found that the resolution of the pressure gauges was difficult to read and not very precise. So there was 8 ticks for pressures marked between 1,000 and 0 psi. And then from 1,000 to 2,000 and 2,000 to 3,000 and so on, there was 9 ticks for the pressure readings. And this gave us a little bit of uncertainty in what the actual value was there that we couldn't calculate as easily and measure as easily. Also for the flexure of the pins and the supporting elements, the load that we applied had some kind of impact and some kind of deformation, which then changed our statics a little bit in real life that we didn't account for. And this ties into our oversimplification of the statics geometries, which kind of arose from incorrect measurements that were just not precise. And also we neglected the relative vertical heights of the connection points, which attributed more to the flexure of the pins. For the dynamic section, we had 49% and 62% for extension and retraction. And we chalked this up to the fact that the pump that's on the excavator has a variable flow rate due to load sensing. And since we were running our experiment with no load on the bucket, it meant that to save fuel and to be more efficient, that the pump only had to output a lower flow rate than the one that we used to calculate on the spec sheet, which is 26.4 gallons per minute, because it didn't need that much fluid going that fast. So if there would have been more weight on the bucket, then we could have seen a lower error here. But for the sake of our experiment and for safety, we were not able to apply any load to the bucket when we were doing the extension and retraction. Thank you all for watching. We wanted to give a special thanks to Dr. Hilten. He's the director of the labs and was able to get us all set up with the excavator. Dr. Thomas, he was the instructor and the overseer for the lab, and really helped us out sourcing parts and getting all the intricacies of the experiment under wraps. Mr. George Haynie, the university's research machinist, he was very helpful in getting our materials set up for our lab day. And then lastly, Mr. Dave Henderson, he was our contact at Caterpillar and helped us design and think about ways that we could get data off the excavator and also how to experiment. Thank you all for watching.